Hello, the topic of this lesson is diagonalization of symmetric matrices. So let's begin with a brief overview of the lesson. So in this lesson, we learn about symmetric matrices. So a matrix is symmetric if it is unaltered by an interchange of its rows and columns. So if you interchange all the rows into columns and vice versa, and you get back the same matrix, then it is symmetric. So here's an example of a symmetric matrix. You see where the matrix A has got diagonal elements 1 and 5. That doesn't matter too much, but the elements over here are equal, so that's a symmetric matrix. Now, these matrices are important because they have some remarkable properties with respect to their eigenvalues and eigenvectors. And even more, they arise quite often in applications such as statistics and data analysis. Okay, so the main point is, of course, that the concept in this lesson will provide the foundations for the following lessons. So for this reason, we actually want to learn about symmetric matrices in quite good detail. So let's begin with the definition of a symmetric matrix. So a symmetric matrix is a matrix such that its transpose is equal to the matrix itself. And so, of course, such a matrix must necessarily be square. So here is a matrix A. You see it's nice and symmetrical. You've got a 1 here and a 1 there, and a 2 over here and a 2 there, and a 10 over here and a 10 there. Let's check that it equals its transpose. That's true. And we have a nice function called symmetric matrix Q, which will tell you whether it's symmetric or not. And in this case, it says true, which means the matrix is symmetric. Okay, now the nice thing about these matrices is that if we take an arbitrary real matrix, then the eigenvalues may either be real or complex numbers. After all, they are solutions of the characteristic equation. But if you have a real symmetric matrix, then the eigenvalues are always real. So for example, here is a symmetric matrix, and you find the eigenvalues. Take the numerical value in each case, and you see that they are real numbers. Or if you take an arbitrary 2 by 2 matrix, which is symmetric, and you work out the eigenvalues, you see that you have a square root over here, but that square root cannot be negative because you've got 4b squared plus a minus c the whole square. So these square roots over here are actually going to be real numbers. Okay, another nice thing about symmetric matrices is that if you take an arbitrary matrix, then the eigenvalues of them have got corresponding eigenvectors, which will be linearly independent, but they may not be orthogonal. But if you have a symmetric matrix, then the distinct eigenvalues have got eigenvectors that are always orthogonal. So for example, here's a symmetric matrix. Let's find the eigenvectors, and let's check that they're actually orthogonal. And also, if you take an arbitrary 2 by 2 symmetric matrix, you can again check that the inner product is going to be 0. Okay, so the main point is that symmetric matrices have got a very nice property, namely orthogonal diagonalizability. So here is a square matrix A, right? And we would say it's orthogonalizable if there's an orthogonal matrix P such that A is equal to P into D into P transpose. So that's the meaning of it being orthogonally diagonalizable. So D is a diagonal matrix over here, and P over here is an orthogonal matrix. And the fact is that A is orthogonally diagonalizable if and only if it is a symmetric matrix. So that's a remarkable property about symmetric matrices. So as an example, here is a matrix. It's clearly symmetric, 12 and 12, 13 and 13, 13 and 13 over here. Let's try and construct the eigenvalues and the diagonal matrix corresponding to them. Find the eigenvectors, orthogonalize them, and you can check now that if you do P into D1 to transpose P, so you got the P from here, the D1 from there, and the transpose of P, then you actually get back the matrix A. So that's a remarkable property about symmetric matrices. Okay, and that leads to what is called the spectral theorem, one of the most important theorems in linear algebra. So if you have a matrix A, Then a set of all its eigenvalues is called the spectrum of A. That's like the set of colors of A, if you like. And if you actually have a nice theorem for symmetric matrices, namely if you have a symmetric matrix, then first of all, you saw early on, the eigenvalues are all going to be real. And in fact, there are going to be n of them counting multiplicities. If you take a particular eigenvalue and look at the eigenspace, then there are enough eigenvectors, so to speak, so you actually have enough eigenvectors to fill out the eigenspace correctly. And the eigenvectors corresponding to this eigenvalue is always orthogonal, we saw early on. And to summarize, this matrix actually is orthogonally diagonalizable. Okay, now we have a nice function called Jordan decomposition, which can actually do that for you. So let's say you have this symmetric matrix over here. You can compute the Jordan decomposition. You need to orthonormalize actually over here. We say orthogonalize, but that's because the matrix is going to be orthogonal. And let's check now that we actually get back the required relation. So Jordan decomposition is a very nice function for such problems. And finally come to the idea of spectral decomposition. So let's say you have an n by n symmetric matrix and you have the orthonormal eigenvectors of this matrix and you have the eigenvalues of the matrix. Then the matrix can be kind of decomposed over here, broken up into simpler parts. You can do lambda 1 times u1 into u1 transpose, etc. Keep in mind that each of these over here will actually give you an n by n matrix, because think of u1 as being a kind of column vector. And this is called a spectral decomposition A. So it's like breaking up the matrix A into simpler parts, which are determined by the spectrum or the eigenvalues of A. So as an example, here is a symmetric matrix A. Work out the eigenvalues, work out the orthonormal eigenvectors. I'm using orthogonalize over here to do that. And then you can kind of do a Kronecker product, like a product of u1, u1 transpose, like you don't want early on, and it's lambda 1 times that. That's the first component. That's the second component. And now you have the spectral decomposition of A. So you can break up A into simpler parts based on the eigenvalues and eigenvectors. Okay, so that's the end of this lesson. And the main point is that in this lesson, we talked about the spectral properties of symmetric matrices. And the spectral theorem asserts that such a matrix actually has an orthogonal diagonalization. That's a very important property. And then you can go a step further and do the spectral decomposition, which breaks up such a matrix into simpler pieces that are determined by its spectrum. So that's a nice way of breaking up the matrix. So we'll use some of these ideas in the next lesson on quadratic forms, but I'll stop over for now. Thank you very much.